BC Calculus, continuation of lesson 5.5, Linearization and Differentials. I had hoped to finish this in the previous video, but things just got way out of hand. So, set this up and it ran away on me. This is linearization, and we're finishing up with talking about other aspects of differentials. The equation differential of f equals the derivative of f of x dx tells us how sensitive the output of f is to a change in input at x. So if it's at a high slope value, you're going to have a great effect on f for any given dx. So just as an example, you want to calculate how deep something is, which is actually a lot trickier because you have the sound has to travel back up the well. But you drop a rock down to the water below, and you want to see how long it takes. So ds equals 32 t dt. And we may have screwed up by 0.1 seconds. So we are looking at ds equals 32. Well, let's try t equals 2 seconds. And we'll try another one in a second. Another one momentarily. Times 2 times 0.1. So if it was a relatively short distance, your mistake would only be 6.4, and this is feet. So, hey, I'm off by 1/10 of a second. Well, don't worry, you're only, you've got it accurate to within plus or minus 6.4 feet. Well, what if we had a t equals 5 seconds? So again, you have the same formula. ds equals 32, but this time times 5 times 0.1. And this time you would be off by as much as 16 feet. So, introducing the topic, we won't go very far with this. Just notice that it can measure the sensitivity. One of the best applications is Newton's method, and it's used on your calculator. That's why you have your calculator says, give me a rough idea where I'm looking at here, and then give me a guess. Okay, I'll zero in on it. So you guess an approximation, and your guess has to be good. Because if not, it's gonna oscillate or it's gonna just go away. I've got some good examples on those for your homework. But here's what it is: your guess, and this is the original function, and this is the function derivative. To give you a rough idea why this works, I'll slap it out here. What's going on is this, and it's a hypothetical situation. You'll have to bear with me. Here's the curve, so you go up, you say here's the slope, and this is f of x1. This, of course, is 0. This will be your new guess, x2. So the slope is f prime at x1, and that equals f of x1 over x1 minus x2. So when you go to find your x2, you're pretty much set based on what's going on here. So we're going to guess, I don't know, we could graph it. Let's go with negative 0.3. So we find the derivative, and we have the original function. And if you're saying to yourself, wow, that looks really nasty, it's funny, I'll say use a calculator, just not the way that you could to shortcut the problem. So it doesn't really make sense, but it'll have to. But we programmed this in. This is the way I do it, and I found this works extremely well. Let's see if I can get this to match up properly. Always a challenge with the calculator. And and that'll do. So I go over here and I put it in here. I say it's my guess, x, because I'm going to put that in, plus, pardon me, minus. Fraction. Function on top, x to the third, plus 3x squared, plus 1. And on the bottom is the derivative, so 3x squared plus 3. And I go to table, and I start at, who cares, 1. And who cares, because I'm going to make this independent and ask. And then I go second table, and we put in, we said we were going to guess negative 0.3. It says, no, it's closer to negative 0.6801, so negative, and actually I've got a mistake in there, so I gotta go find it. Minus x to the third plus 3x squared plus 1, x minus all over 3x squared plus 3. So it actually looks good to me. I'm not sure what I did wrong. X to the third plus 3x plus 1. Aha. It's not squared. Lots of room for mistakes here. Enter second table, which is annoying because it still has that thing there. But there it is. It says, looks like negative 0.3 is close, but not quite. Negative 0.3223. That gives me negative 0.3222, negative 0.3222. And it gives me the same one out. So then I know that I've settled on an answer. So x was actually 3, I think. It's negative 0.322. Doing that the long way by hand would be challenging, but doable. So let's finish up. And we look at how the graph actually looks. I'm going to turn this one off because when I graph it, I don't want it to show up. And the original graph is x to the 3 plus 3x plus 1 graph. Only hits the one spot. Second calc, I want a 0, 2. So again, this is what Newton's method is with the calculator. Pick a spot left and right of it, just to give me some parameters. Give me your best guess, and it finds negative 0.322. So that's Newton's method. Not too bad. Note, Newton's method does not always work. I believe it's problem 26 in the homework, where it gets worse and worse and worse. So give that a shot. You might actually go find the other root, and you didn't realize it. And you might do something where it oscillates back and forth. So there's lots of options. But regardless, get cranking, and happy mathing.